the Unitronics webinar. Can someone please let me know if they can hear me? If you guys can hear me all right, just send a quick message. Just in the little chat, if anyone can hear me. Sounds good, I can hear you. Yep, okay, great, thank you guys. So today is June 8th. Thank you for coming. We were doing a webinar today on some Unitronics VisiLogic tips, debugging, and programming tips. So a couple little things that Jason and I kind of do regularly. Hopefully we can share some insight on how to get around the programming environment a little better, a little more comfortably, and hopefully solve a couple problems that are common problems. I'd like to say thank you for coming again. This is now over the 10th webinar we've done, and of course we have our Unitronics webinar library. If you go to www.unitronics.com/webinars with an S, we've been hosting all the webinars we do, recording them, and posting them with the applications. So if you haven't seen those, you can go, feel free to check those out. Again, if you have any requests for future webinars, please let us know that. Next week we'll be doing a webinar, I'm sorry, not next week, in 2 weeks on GPRS, SMS, and GSM wireless cellular modems we provide the Infor kit. That being said, let's go ahead and start today's webinar. I have an example application I wrote here that we'll be going through. There's 5 or 6 different sections to it, so we'll step through one by one, but I'd just like to point out that if general programming guidelines, what we want to do when we're programming with anything really, we're giving descriptions to variables. We want to try and make these descriptions the best we can. This way, when we are coming back and debugging either our own program or someone else's, we'll have as much information as possible. If we don't give any descriptions to a bunch of memory integers, it's going to be very difficult to remember which is which. Maybe even impossible to get the program to work if for some reason something is not working correctly. That being said, let's dive into this program, assuming we don't really know anything about it. So let's take a look at the first net now. By the way, I'm using the V570. I'm going to go online here and just bring up the controller. We can see what's on the HMI. In 1 second. There we go. Make it a little bigger. Okay, so we see our controller view. These 4 sections are all different parts of the program, and we're just going to be concerned with the upper left right now. If we look on the left, we have nets 1, 2, and 3 here. We see that we have a normally open contact of MB0, 1, and 2, and they're all connected in series to a coil for MB10. Notice all 3 of them, all 3 separate nets are connected to MB10. What we have on the screen is a status message, a binary, which is going to display either MB10 low or MB10 high. And we have 3 buttons to press here. Now, just off the bat, if anyone wants to send a quick message, let me know. Maybe you can use the raise hand if you see that there is a problem with the setup. If you think it's okay, let me know that too. Hopefully I'm giving away a little that there could be a problem here. Okay, so let's take a look at the program we have here now. Notice we have MB0. If I press it on the keypad, MB0 goes high, MB10 is still low. If I press now MB1, we see that MB1 has gone high. We should expect MB10 to be high, but it's still low. We press MB2, we see MB2 has gone high, and now MB10 has gone high. So there's a fundamental portion of this program that we need to understand before we can go ahead and create simple nets like this. Now, does anyone know what the problem is here? Go ahead and just send a quick message if you understand what the problem is. I'm going to leave online here, and I'm going to open up our help file, and I'm going to search for a program Oops. And let's take a look at this nice help file entry called the program sequence. Now, before we can understand what the issue is, we have to understand what the PLC is actually doing. The PLC works in a scan. It starts processing from the first net and runs all the way down to the last net. And that's about as simple an explanation as I can give. What's really happening is when we start one scan, the beginning of the scan, we can follow this map here, is it's going to read the physical inputs. This will be the inputs we have in the system. We're going to start running through our nets one by one. So if I slide this over a little bit, oops, let's see if I can put it on the other side. We can see that our net 1, our net 2, and our net 3 have been executed in order. Now, if MB0 is high, we should expect MB10 to be high. So in our first net, we can say that it is high. But in the next net, if MB1 is low, MB10 is now going to be set low. And in net 3, MB2 is low, MB10 is still going to be low. So really what we have is some conflict going on here in the ladder. It is true that MB10 was high after the first net, but nets 2 and 3 put it back to low. So we're never going to actually see it here. So if we go back to our scan, we can understand that things are going to execute in order. There's a little more explanation here as far as subroutines go. We'll take a look at this again in a bit, but to understand what's happening, always keep in mind what the controller is doing. It's starting at the top and it's scanning all the way down. Now, what is the solution for this? Let's go ahead and let's scroll down a little bit. Notice I have another net here set up a little differently. I notice that in the first one we had 3 separate nets and they're all in series, outputting to MB10. Below we see a simpler solution. We have a single net, inputs MB0, 1, and 2 are all in parallel, and they're all connected to MB10. So if you notice also on the left, this is greened. If I right click, I can select Enable, and I'm going to scroll up a little bit, and I'm going to right click here, and you can see we have a Disable function. Now the Disable function is very nice. It allows us to stop portions of the code from being downloaded to the controller. If we use a Disable, and I'm going to go ahead and disable these 3 nets, we haven't actually made a change to the program in the PLC. We still have to download it. But if we're working on our desk or we're debugging in the field or really anywhere we have the program, if we have a section of code that we don't want to execute, instead of erasing it, we can disable it and we can keep similar nets, maybe 4 or 5 in some cases if we're trying to test out different things, and we don't have to execute them. So I'm going to go ahead and download this and we'll see what happens.
Welcome to GoToWebinar, web events made easy.
Again, I'm just using the online test. We can do that, or we can hit the F9 key, and I'm using remote access to bring up the controller view. You don't need to bring up the controller view at your desk if you have the controller there, but say you are working remotely over Ethernet on a controller a couple states away. It's a very nice option to be able to bring up. Now I'm going to go ahead and press, let me scroll down on this one first. We can see our parallel network, MB0, and now MB10 is high. Notice I'm only pressing MB0. I'm going to let go, and now MB1, and the status is high, and MB2, and the status is high. Now this, I would say, is the, for a beginner especially, the first, simplest, easiest mistake to make. If we want to have several conditions all activating a similar output, we're going to say, okay, just running through the logic in our head, I'll have this condition, and then we'll have this output coil. And then I have another condition, and we'll have this output coil. It's very important to group these. Again, we've made a parallel network here with a single output. We're not battling each other. Everything is working together. Okay, is that clear? If anyone can give me a little feedback or questions. Okay, great. So while we're here on this example, I just want to show a couple more functions in VisiLogic. Now, if we open this program and we did have absolutely no knowledge of it, we would see that there's a couple inputs, MB0, 1, and 2, but where do they come from? Notice the description. This net shows 3 contacts sharing the same coil and the same net. It's a nice description, but it doesn't really give us all that much information about what's going on here. So, if we right-click, notice we now have a couple options, and one of them is Find MB0. I'm going to select this. We notice below we have a little menu now, the Find function, and it's displaying everywhere that MB0 is referenced in the program. Okay, so we have a description, main module, main routine. This is our main routine, and our net number, net1, and the element type. It's a direct contact. So if I scroll up, you notice that this is the one we disabled previously. I don't have to scroll to it. Also, I can just click, and it'll bring us to the appropriate location. Of course, net 5 here. This is the one we searched for. So we should understand that this is where it is. But now we want to see the other places. We notice we also have the startup module, the startup display, and it's a button, and it's linked to a touch element. So if we click here, we'll be brought to the HMI and to the specific variable, or in this case the button, that MB0 is linked to. Now this is very valuable, especially if you are looking through someone else's program and you're trying to get a feel and understand what is going on in this application. If we have a lot of contacts and a lot of coils sharing bits, especially multiple contacts sharing the same memory bit, it's very nice to be able to just click through here and see where each one is I'm sorry, where each one is in use. Doing this also, we can follow a whole trail back to the beginning, basically, of where the main function that's activating these bits. Okay. The only other one thing I want to point out is we were using this online test mode, and I feel most people should be familiar with it. It's a very, very valuable tool. Again, I can click here, or I can click F9, but this is our online test, and what it allows us to do is see what the controller is actually doing. So we can view, for example, if we click on operands, the status of all the memory integers and the bits and all of our operand types, and then just the menu on left that allows us to select. So let's go to bits, and we see if we scroll all the way up, oops, all the way up, memory bit 0, 1, and 2 with their descriptions, and we see in the glasses these blue values are their current state. So if I press the button MB0, we should see that MB0 goes high. If I press the button MB1, we should see MB1 goes high. Okay. So again, these are the basic tools we use to go through and see what our program is doing in the controller. Okay. Let's go down to our second example now. And I'll bring up the controller view again. Okay, so net 7 here, and I've just spaced them out. It doesn't really matter that we've left white space in net 6. Net 7 is a normally open contact of MB20 to an incrementer function block linked to MI0. We notice we're on the online view right now. This blue value means the value in MI0 is 0. I can click, and I have our little editor option, so I can put a new value in. And if there's nothing wrong with the logic stating I can't put this value in, it should let us put it in. Okay. Again, a nice little online tool. If we have a function that needs to count up to 100, maybe it takes some time, we don't want to wait for that whole process, I can just come in here and put 99, and we can jump through our process, another debugging tool. We'll put it back to 0. Let's explain quickly what the incrementer function block is. Every scan that it's pulsed, the incrementer will add 1 to the register it's linked to. So in this case, every scan that the incrementer block is pulsed, we're going to add 1 to MI0. Now I want you to look at this net. It's very simple, two function blocks here, and just decide what you think is going to happen when I press down on this button. I'm going to press and hold it, and just try and get an idea of what you think is going to happen. Okay, has everyone made up their mind? Let's go ahead and press and hold down the button. We notice that the numbers seem to be jumping up erratically. Okay. They're actually jumping a lot smoother, but because of the online view, we're updating periodically. So what's happening here is we're activating this function block that's designed to take a single scan and increment this value once. If we go back to our help file, our diagram here, we notice that we're going to check an input. We're going to run through and activate that net if it's applicable, and then we're going to exit at the end and come through and do it again. Now this all happens on a rate of about 1,000 times a second for a small program. Program such as this, I would assume about. What we're doing with this normally open contact is we're energizing this incrementer function on every scan. Okay. Now this is probably not the functionality we want to have with this incrementer block. If we wanted to say count the amount of times we press the button, we could replace this, and I'm going to leave the online test. We could replace this normally open contact of MB20 with a contact that should work better than that. Now if we go to contacts, we notice we have a positive transition contact and a negative transition. What this will do is activate on it as soon as we press it, and only for that one instance that we pressed it. So it's actually the transition from low to high that it will be enabled. Now I can come down and click and put this and link it. But if we want to look at some of the other functionality we have available in VisiLogic, we can use our right-click button. And notice that we have two areas here. We have this description, our variable area, and we have this schematic area. They're actually different. I can click on each of them. If I click here and try and drag, I'm clicking with my left click and trying to drag. Notice I can't move the can't move the contact. If I click on the schematic portion, I can drag this around everywhere I want. So they are two separate sections in VisiLogic. I'll right-click on the top. We notice we have options pertaining to MB20 here, our fine that we saw earlier. Now if I right-click on the schematic portion, notice we get other options. These are things that pertain to that contact. So one very nice thing is we can replace ladder elements of similar types. So if I'm experimenting here and I have a normally open contact, if I want to replace it with a positive transition, it's very easy. I just come and click, and I've replaced it. Now again, remember, what we're doing is changing the program. We haven't made any change to the program in the controller, though. To do that, we're going to download again. Okay, so our download is complete. Let me bring up the controller view one more time. And I'll press the button just once. Notice even though I'm holding it down and it's still activated and high, it's only active for one scan. It's only putting out one pulse to the incrementer block. So I'll let go, press it again, and let go, and press it again, and let go. Now, if the concept of the positive transition is new to you, I would recommend watching our beginner lights and buttons webinar. But the point here is just to illustrate the functionality that's available with VisiLogic. If we right-click, we have these other elements and tools available to us. Okay. And again, this should illustrate the idea of the program scan. If we see this counting up and at a crazy erratic rate, we know that the net is being activated more than once. So that should help us deduce that we have a problem. If we have a function, say a communication function, we want to issue just one command, If we place this incrementer block on it and it starts counting up at a very fast rate, we'll see that we're not activating it just once. We'll see that we're activating it many times. Now I have one question. Does the PLC scan top to bottom, then left to right, or does it scan all inputs top to bottom and then changes the outputs? Let's go back to our schematic here. Let me open it up again. What we do is scan the inputs. We create an input table. We run through the ladder logic. We execute the nets that weren't being executed. What do I mean by that? If you have a normally open contact linked to MB0 and MB0 is low, we will stop scanning that net. All the conditions that are after it are not going to be activated, so we move on to the next. If that MB0 was high, we would execute that net and move on to the next. So we execute all the nets. We'll talk about the subroutines. We update our physical outputs. We process our HMI, and again we'll talk about this in a minute. We process our communication, and that's one full scan. Then we loop around and we do it all over again. Okay, can everyone let me know if we're okay so far, or if there are any questions? I'll assume silence means we're okay. Good, okay, great. Let's move on to our next example. I'm going to pull up the HMI again. Notice example 3 here is net 9. This is a subroutine call. We didn't really talk about the subroutines, but we will in a second. Let's just take a look at the problem here. So in our third section here, we have the start timer button. I'm going to go ahead and press it. And I hope you can see how fast it's ticking down. Maybe I can show you this way too. It would look a lot smoother, or rather it does look a lot smoother on the HMI. Timer 0. But what you're seeing here is a 20-second timer that's counting down twice as fast. Is that clear to everyone? Can everyone make that out? Okay. Now, the timer preset is 20 seconds. Why would it count twice as fast? Does anyone have any idea? If you have an idea, go ahead and type it into the questions box. Okay, Barry, thank you. So Barry says that it's being activated twice, 2 coils. That is correct. If the proper function, the proper use of a timer is to activate it once per scan. If we activate it twice, we'll count twice as fast, three times as fast, and so on. I'm going to leave the online view, and let's take a look at what we have. So all we know from here is that we have a timer 9, and we had a button on the HMI. I'm going to right-click on timer sub, and I'm going to select Find Timer Sub. And we can see, well, of course we're going to know where the timer subroutine is, but we can see that it's being called from net 9, which is where we searched originally, and it's also being called from the startup module. All right, let's take a look at what timer sub is. Very simple network here. We have a single button MB4, and it's running a very nice timer arrangement that allows us to cycle a timer and output 1 pulse. If you haven't seen this, you can check out our timers webinar. If you're trying to create a simple cyclical timer, this is about as nice as arranged as you can get. And if you don't want any control, if you want it to run forever without anything turning it on and off, we can just do this. What we're doing here is the bit value for timer 0. If it's low, it's going to activate the timer coil. As soon as it goes high, the bit value for timer 0 will be high. We can use it maybe below in a contact. As soon as it comes around and it sees that TD0 bit is high, it resets the timer and then it runs again. So this is an endless 20-second time base 1 pulse. Okay, let's take a look now at the HMI side. Notice we clicked here. If we go to our links and jumps, we see that we have a timer subroutine being called while this display is running. So we have two instances where we're calling this subroutine. One is from the HMI, and one is from the ladder. So what we're really doing is we're activating this timer twice per scan, and we're counting twice as fast. Okay. So the first thing we did here was notice that the timer was not working correctly. We know that the timer is running in the subroutine. So again, if we search for the subroutine, we can see that it's being called in two places, and we can fix this problem. We do want our timer to run at 20 seconds. What can we do? Well, we can either stop it being called from the start of the display or stop it being called from the ladder. At this point in this example, it doesn't really matter if the subroutine was pertaining to that screen specifically. Maybe we want it to stay linked to the screen, and maybe we just want to delete this. If I download now, okay, and we'll take a look at our online view again. We can see our timer is running at the correct rate. Okay, is that clear? Is there any questions on that? Okay, let's take one more second and let's look at our our program sequence again. Again, we said the inputs, we check them and we form a map. We come into the main routine. Now, we didn't talk about the subroutine calls, so let's talk about them now. In this description here, we have a subroutine call in net 3 to subroutine X. Notice that we jump out of the main routine right at that point and start executing subroutine X. In subroutine X in net 3, there's a call to subroutine Y, so we'll jump out of that, execute subroutine Y. In subroutine Y, there's another call to subroutine A. We jump out there, process subroutine A. Subroutine A has no more subroutine calls, and it would get to the return. Now, the return statement is in every subroutine and even the main routine. It's the last thing you see at the bottom of the main routine. When we hit the return, it signals us to jump out and to return back to the original call. So we'll return to that call, execute the rest of subroutine Y, hit the return, jump out, execute the rest of subroutine X, hit the return, and execute the main routine until we get to the main routine's return. Now, we notice that one thing to point out is we were running the subroutine from the ladder. We were calling it from that net 9. And we also had it linked to the HMI. When we have it linked to the HMI is updated after the main ladder is executed. So that subroutine is actually going to execute in this portion of the scan. So it's just something to understand. Again, a lot of these debugging problems or debugging issues, sometimes they seem like they make a lot of sense when we're programming them, but if we don't understand the underlying execution of the program, of the PLC, it's going to be very hard to determine what the problem is. So again, good descriptions, thinking before we do something, and good knowledge of the tools and the functions we're using. If we don't understand what the PLC is doing, we're bound to make endless mistakes, assuming that something else is happening. And that really goes for any computer, any processes. Okay, is that all clear? Is there any questions? Okay, the next nice tool I want to show you is the watch tool. What I've set up here is a pulse width modulated output PTO configuration. I'm going to go to the hardware configuration. You notice that I've selected the snap-in, the E3X, actually 4X. If I go all the way to the right, we can take a look at the high-speed output PTO. Notice I've set this up for output 0. If you're not familiar, the high-speed output PWM It gives us the option to select an operand for the frequency, an operand for the duty cycle, and a run bit. When we set the run bit, we're going to output pulses at the frequency we've set with the duty cycle we've set. So, in a quick example here, we've set the frequency to 100. The duty cycle says 500. This means 50%. We expect a 24-volt square wave that is high and then low at the rate of 100. For the PTO, we have two more options. We have a target and a current position. So these are two more variables. With the PTO, the pulse train output gives us is the ability to set the target to 1,000 pulses. When we hit run, we will output 1,000 pulses at this frequency. And we can see the current position here. Now notice we have two memory integers, a memory bit, and two double words. So these are mixed data types. They're all relevant when we're working with this function. And if we're working on our desk or we're out in the field debugging, we want to be able to see these all grouped together. Okay. So again, this is just the hardware configuration. This is where we have linked these values to. I'm going to hit OK and exit here. Now again, we notice from our operands, we can browse to all of our different register types. We can select memory bits and we can view the run MB for PWM. So we can go here again if we're online. And we've got the ability to see its current value, which is 0. And if I click on it, I can set it. But if we want to also monitor the frequency, then I have to go to our memory integers and find our frequency and our duty cycle. Oh, but I want to see our position as well. We have to go to our double word. Now notice if we right-click, we'll select target. We have the option to insert the register we clicked on to a watch. We have 8 watches available. If I click watch 2 here, we'll go to our watches right next to operands. And we'll click watch 2. And we'll see that this is what I just added, double word 1. Now I've already added all these registers to watch 1, and it's very nice. We now have a grouping of operands that are relevant for this process. Okay. If I want to be able to monitor all these things and make changes to them at the same time, I can do that. I can see this information here. So let's go ahead and we'll select the run bit. We've put in our frequency, duty cycle. Our target is 1,000, and we can monitor all these different operand types at the same time. So we want to watch this current position, and I'll just set this. Notice it's counting up at 100. We want it to go faster, so I'll put in 200 now. It's going up faster. Okay, we'll put in 500. It'll zip to the end very quickly. Okay. Anyway, the point isn't the PWM as much as it is to see that this is a useful tool here, this watch window. And we have 8 available. And you can group like items that you want to monitor in each of these watches. Okay. Again, to add something to the watch, we just right-click and select Insert to Watch. Okay. So is that clear? Does anyone have any questions? No? Okay, great. Let's go ahead and take a look at our next function, or I guess example. I want to stay online. And I'm going to go back to the controller view. Let's just take a look at the screen and see what is going on with this. Notice on the bottom here we have 3 binary image variables, 1, 2, 3. They're all blinking. Now, the intention on programming this is that each one of these would blink. Each would sequence through the next, 3 seconds on each. So we should see green, green, green. That's obviously not what's going on here. So this isn't my program. I'm not sure exactly what's going on. Where is the first place to start? Well, let's go ahead and figure out what these binary images are linked to. I'm going to leave the online view. I'm going to go to the HMI. So what we're doing now is walking through the process of debugging here. So we have 1, 2, 3 binary images. We can double click. We can look at the values, red and green, linked to MB6. Okay, MB6. This should be the bit that decides whether our display is going to be red or green. Let's take a look at the next one. Notice I can hover over 2, and it'll tell us what bit it's linked to. MB6, MB6, and MB6. Okay, so they're all linked to MB6. Maybe this is our first mistake. Maybe someone made a copy and paste error. If you don't know how to use the copy and paste, let me explain real quick. We can click on a variable. We can select copy. If we select paste, notice we get an error. You cannot paste this selection. There's already a variable in the space. The way this works is we need to move the original to a new location, and we can paste the new one in the same location. So if we look at this variable now, notice that it's got the same exact bit, MB6. Maybe the programmer made a mistake. Maybe they copied and pasted, but they forgot to change the bit it was linked to. It's a common occurrence. If we're copying and pasting, maybe we copied 100. No, I'm sorry, that's an exaggeration. Maybe there's 10 different variables, and they all end up having the same bit linked to them. We have to understand that our copying and pasting is taking all of the variables we have linked to it. Okay. So we know we're looking for some function that's dealing with MB6. If I want to search for it, I can come over to our memory bits from our operands. If I want to go to a specific memory bit, I can right-click and select Go to Address. Maybe it's 524, that's far away, I don't want to scroll. So I'll type in 6, and it'll bring us to MB6. Also, we have a pair of binoculars up here. Notice these are different than the glasses. This is our Find tool. It's a very nice tool in that it allows us to search for all of our different operand types, constants, shared networks, labels, subroutines, and displays. Also, it allows us to type in by description. So if we are looking for, what did we call it? Step 1, STEP. Notice that we now have a list of all of the different operand types that have the letters STEP in their description. This, again, is one of the most beneficial reasons that you should use good descriptions in programming. Just because it's easy now to find the things that are linked to the functions we're interested in. Okay. But anyway, let's go to MB6 here. We can click, and we see that we have a network now, which is in our main routine, and it's linked to this series of sequencers and timers. Now, from looking at this, maybe we'll deduce that we made a mistake already. We figured out in HMI that all the values are linked to MB6. But what do we need to change them to? Let's go ahead and look at the main routine and try and decide. We have MB6 as a contact. It's going to run a timer. When that timer is up, we're going to set MB7 and reset MB6. Okay, so MB7 is now our value we're going to display. It makes sense here if we look at the structure that we have MB6, 7, and 8 that we need to use for our display. Let's go ahead and we'll go back to the main display. Let's change this to 7. Okay, and we'll change this one to 8. Notice it makes sense now. Someone programmed it right. Well, we think they programmed it right so far. They gave it the right description, step 2 and 3, but they made a mistake on the HMI. Okay, so let's download this now and let's see what happens. Again, what we're trying to do here is take the logical steps we would have used to create these functions and figure out where the problem lies. We did our first comparison, or our check rather, on these 3, and we saw that they were linked to the same thing. Now we look at them, and we see that we have 6, 7, and 8. We analyzed our function quickly, and we determined what the right values were. So let's go online and let's take a look at what's happening now. All right, our first light is lit. 3 seconds later, our second light is lit. And 3 seconds later, our first light is lit. Okay, that's probably not correct. At least we made a difference, though. At least we're seeing now some of the functionality is working. We see the light 1, we see the light 2, but light 3 is never lit up. We've exhausted what we can do on the HMI side. So let's go ahead and we'll look at the code to see what we can figure out about it. I'm going to leave the online test and go to the ladder. Now I'm going to give you guys all a second just to look at this, and if you think you can figure out what the problem is, go ahead and send me a message and let me know. I'll give you about a minute to do this. If you don't think you can figure out the issue, in fact, don't even worry about the issue so much. Try and figure out the process that you would use to figure this out. If you can look and analyze it, this isn't a terribly complex network, so we should probably be able to figure it out if we understand timers. But if it was more complicated, if it used a bunch of subroutines and functions that were all over in different networks, it might be a little harder to figure out. So one useful tool we can use is the incrementer function block. We know that we have 3 different variables that we need to go high. Let's go ahead and we'll put this incrementer here. We'll give it a new memory integer, and we'll give it a startup value of 0. We'll put 1 here as well. Oh, I'm sorry, I'm putting them in the wrong place. Come on. And we'll put 1 more here. Now they're all different. They're all going to start up as 0. Let me go ahead and download this, and we'll take a look at what's going to happen. Okay, so we've downloaded. Notice that we have MI 9, 12, 13. They all have a 0 behind them. Again, this was our startup value of 0. I want to make sure that all these incrementers start with the same value. This way we can see if there's a discrepancy between them. So we'll go online and we'll just view these values now. We see that we have 3, 3, and 0. So we see already there's a problem here. We want to watch them increment. Since this is a simple sequencer, they should increment in order. We have 5. And now we have 5. So we should expect to see 6, and then 3 seconds later 6. Okay. One thing we can do as well, we can click on the timer, and we can see its current time and its preset time. If we wanted to inject a new time value for the current or preset, we can do that as well. But we can determine that this rung here, or this net 16, is not being activated. Okay. And so I see some of you figured that out already by looking. That's great. Thank you. And now we have a tool that's showing us that this network was not activated. So let's go ahead and take a look at what is going on in this network, in this ladder. Again, maybe someone used a copy-paste function. When we use a copy-paste function, we remember that we've taken those specific variables that we've linked to. Maybe we like the structure. We've copied these 2 nets and pasted them down here. Maybe we just forgot to make 1 change. So we see that when MB7 is high, we run timer 2. Timer 2 will be high for 3 seconds. The bit value will activate timer 2 contact. We'll set MB6, and we'll reset MB7. Now, this probably worked well when there was only 2. MB6 was the first one, but we forgot to set MB8 in this case. So let's make a change here. I'm going to leave the online. I'm going to change this to 8. And let's take a look at the rest of the logic. Reset MB7. Good, that was the function that was calling it originally. Now we have 8 high. We run this timer 3. We set 6 and reset 8. Good. So that looks like it makes sense logically. Let's download this. Okay, we've downloaded. Let's go ahead and let's go online. And let's look at our controller view again. Again, these are simple examples, but the process is really what's important here. The thinking logically about each step we're going to take and how we should expect it to work. Now, a lot of times when we expect something to work one way and it doesn't, the base cause can be maybe we don't understand it as well as we thought. Maybe we made some assumption. So going back and reading the help files or doing a simple test, actually one of the nicest things you can do is create a new project and build just that functionality to see if that is working how you expect it to. Again, if you don't have the correct knowledge of the function, and again, that's not to say anything bad, but maybe we haven't learned its particulars or how it actually works, then we're not going to be able to use it in a more advanced case. So we see our first light, second light, third light, and first light again. Great. So we have gone through and we looked at this application that we didn't have any knowledge of, and we've gone through and deduced 2 problems that we had. The first one was the variables all linked to the same bits. The second one was the values were just the the bit was just never being activated. Again, this is one of my favorite tools I have. Available, this incrementer function block, because it's very simple and you can use it in many different places, and you just have to monitor the values. What we want to see is they're all counting up together. Okay, so 37, 37, and 13. Good. Now we should expect this to increment. Okay, so is that clear? Does anyone have any questions on that? Please let me know. Okay, no questions. Let's go ahead and I will leave online here. And we're going to look at just one more example of, of debugging something. I set up a nice little communication function here. This is Modbus IP. So we're going to look at 2 things. First is Ethernet, and the second is Modbus functionality. Very simple. I have a V130 sitting on my desk. I've set up with the IP address 10.2.2.56. It's listening on port 502, and it is a Modbus slave. I'm just going to use this 570 application to connect to it, and then we're going to try and read a value from it. We have a webinar on Ethernet, and we have a webinar on Modbus. Please feel free to look at those if this example, any part of it is questionable, or if you have any questions about it. So let's go online here. Okay, just to explain quickly, system bit 2 is our power up bit. This is high just for the first scan of the control. So just when we start power up, will this net be activated? Generally, we try to put this in the first net, but for this example, I wanted to separate it and group it. So we have a PLC name, which is 570. I can show you the IP address is 10.2.2.55, and the correct network settings for my network here. The socket in it, we're using socket 2, TCP, port 502, and this is important. We've set this one as the master. The V130 we've set as the slave. Okay, and then a Modbus config. Very simple. Socket 2, network ID 255. Again, not relevant right now. timeout 100, retries 3, function in progress bit 9. Again, that's important, we'll use it. And the slave we're going to connect to is the 130 at 10.2256 on port 502. So just to recap the settings we're using here. And go back online. Notice I didn't show you any HMI here. It's because I didn't create an HMI to work with this function. All I need here is online test in my mouse, and I can interact with this as if I had a touch screen. In fact, I don't need the touch screen. I'm just working on my desk. So we have a simple connect function block. When MB11 is high, positive transition sets MB12. When MB12 is high, if the card is initialized, if the socket 2 is initialized, and we are not connected, again, system bits here for Ethernet, we can run this TCP/IP connect and then reset MB12. I apologize if you hear that dead space. I'm muting it so I can cough. Anyway, let's go ahead and let's set this MB11. Again, I don't need to actually have a button on the screen or any physical input. We'll set it. Good. We notice that MB12 has been reset. SB149 is high. We can see that here, that it doesn't look green because it's in an inverted contact. Again, if we want to see our operands, we can go to system bits, and we can go to address 149. We can see that Ethernet socket 2 is high. Okay. Now, we're connected to our slave. Let's go ahead and let's try to, let me just zero this out. Let's try to read from our slave. We have our MB13, which is now our button. Sets MB14. MB14 is high. There's no function in progress, and if we're connected to on socket 2, we should use this read holding register number 3 to read a value. And we're just going to read 0. If you're familiar with this Modbus command, we're just going to try and read memory integer 0 from the slave. Reset MB14. So, interesting values with Modbus, and again, if you watch the Modbus webinar, you'll know these, but we have a status message, total sessions, and acknowledgments, and just quickly, the status message will give us the status of the Modbus command. The total sessions will tell us how many times we've tried to perform this command, and the acknowledgments are the successful completions of this command. So what we want to see is that the status message is 0. This means it's working. The total sessions and acknowledgments should not be out of phase by more than 1. If the total sessions counts up to 6 and the acknowledgments is 0, it means we've tried to do 6 reads, but we've completed none. We want to keep these in sync. Let's look now at the help file. Just make this a little bigger. So what we want to look at is the status message. That status message I said was 0. Well, what if it wasn't 0? What would it mean? Let's go to ladder, FB library, communication, and Modbus IP. And what you'll become familiar with is the more you look at the help file and the enhanced functions, is that they all have some kind of status operand. This is a table of the status messages. And again, if you've used Modbus or any of the commands, you'll be familiar with this, but it's something that you absolutely need to understand is available. The status message is giving us feedback on what the system is doing. So a status message of 0 would mean that our Modbus communication is okay. If we have any other number, we can come reference it here. Common, especially for serial communication, is a number 4, master timeout, and then a number 5, no communication. So if we had straight communication failure over RS-232, we would see a 4, and then we would see a 5. Okay? So let's take a look at our function when we try and run it here. I'm going to set MB13. What we should expect to see is MB13, we'll set MB14. We shouldn't see this really go high unless there's some issue. We should see the total sessions and acknowledgments increment by 1. Maybe some value should show up here if MI0 is not 0 in the slave. So I'll set this, and notice what's happened. We don't have any values incrementing here at all. The status is still 0. What does that mean, though? That means the status is OK. Now, that really can't mean the status is OK. The function hasn't even activated. I'm going to give everyone 1 second, and just tell me by looking at this net 21 and 22 what you think the issue could be here. And I'll just slide this over. Thank you, Barry. Okay, so in my haste as a programmer, trying to run through functions I've created hundreds of times, I've made a mistake. If we want to look at the mistake, notice that we used SB149 above here as a normally closed contact. What that means is it's only going to be activating this network if it's low, but we see now we have it in net 22 as well, SB149 as a normally closed contact. And this means if we're connected, we're going to disable this function. The whole reason of putting SB149 here is to disable the function if we are not connected. So what I did in my haste, I copied and pasted and I stuck it here. I screwed the whole system up. There's no way this can ever work. Forget the status messages. I made a logical error here. So I'm going to leave online test because we can't edit an online test. I'm going to right click. Again, I can replace with a similar type. So I'll put a direct coil. We'll download again, and we'll see what happens. Okay, I'll go online again. Make one quick change for illustration here. Let's now try and connect again. Reset, connect. Okay, good. We see now SB149 is direct, and it's going to allow us to perform our function. Remember that we use this this set system here, so you notice that we performed one read already. Let me just zero these all out. And I'll zero this contact out. Now, I've changed, for the purpose of demonstration here, the value we're going to read to the hex value A000. What that is a system long. This is a 32-bit register. So if I now want to try and perform another read command, okay, I'm sorry, let me change it to something else. Okay. What we can see here is if I try to read a memory integer, I'll just put 0 as the address. Again, if we want to understand what this is, we have the slave address table available in the help file. We can look at the enhanced series. In our number 3 command, the offset for memory integers is 0. But what I've put in here now as a D000 is a timer current value. This is a 32-bit register. If I try to perform a read now, notice that the sessions is going up. The acknowledgements is not. Our status is now 8. So let's take a look at the status message of 8, again status operands, and we'll scroll down to master to application illegal data type quantity. What does that mean? Well, this function worked nicely when I was reading a single memory integer, but when I try to read a single 32-bit register, we get a status message that says it's not working. and we get a total sessions, which is incrementing, and 0 acknowledgments. Again, let me put in 0 here. So the point I'm trying to illustrate is the function type is meant to read these operands. So that's okay. I can read a memory integer. We can see the total sessions, acknowledgments incrementing. But now when I try to read something else that the slave address table tells us should be okay, again, let me bring it up here. D000, timer current. We get an error, and the total sessions increases without the acknowledgement. So what we've done using the right type is create a problem. Now my vector length is set to 1. That would mean one single memory integer. So what I've done here is use the function incorrectly. And we can determine this by our status message 8 and our total sessions. So this is another way of looking at the feedback from the system to determine what the problem we're having is. To fix this, I should set the vector length to 2, and we should read the value correctly. Okay, so we're kind of running a little over on time here. I do want to save some time for questions if anyone has any, and I just wanted to re-illustrate a couple points. The most important thing with debugging is understanding how the system is going to work, or the system works. If we think it needs to work one way and it actually works another way, we're going to have a hard time determining whether it's a logical error or a system error or just a programming error. There's always a lot of ways to do something, a simple task. It's really important to think about how you're going to create some function before you sit down and just write it. Experimenting is great, and I think the Unitronics system here is a great way to experiment because of this online test. You can get all this feedback. But learning the tools, giving good descriptions, and trying to think before we create something is the best key to success in programming. When we're debugging, assuming we have no knowledge of the program to start is a very helpful way to go about it. If we assume and we read the descriptions, if we try to debug based on descriptions, well, maybe the description doesn't match the logic of the net. So we should assume we don't know anything, and we should follow our tools. Our find tool and our search tool are very important. Our watch windows give us the ability to group the functions that we want to monitor in one simple place. I've got just a couple other things I want to point out. One other thing that is very useful and might seem trivial is if we select all these nets, we can just hit Control-A. We can right-click and select Minimize Height. If we do this, we'll minimize the size of all the nets, and we'll be able to see more. For example, if I drag this here, and drag this here, drag this here, I can only see maybe 2 of these on one screen. If I minimize, I can see more. And I can also rearrange things and double-click here to minimize again. So this helps. Seeing more on the screen is very helpful. Okay, so I'd like to wrap it up there. If anyone has any questions, please send them. We'll keep this open for another 10 minutes. Again, thank you very much for coming. These webinars are really growing in popularity, and I think the topics we cover. If you'd like to see anything, please let us know. Send us an email to support@unitronics.com. Again, in 2 weeks we'll be doing one on cell modems, GPRS, and SMS. And we'll be announcing several more for the future months. Again, thank you very much, and have a good day.